All right, so in this video, we're going to be talking about Learning Objective 2-4. And the learning objective itself says to design and conduct an experiment to discover Newton's second law. That experiment is what we're doing with the cart and the string and the masses. And so to truly meet this learning objective, you have to do the experiment as well. And through your experiment, you should identify that if you increase the force on the cart, it's going to accelerate more. And be careful about how we're using those words. Accelerate means to sort of gain velocity, consistently increase your velocity, or consistently decrease your velocity. And if you add more mass to the cart, then it's going to have less acceleration for the same amount of force. So what we're really going to talk about in this video is some more like depth behind that. You guys have done the experiment. Hopefully you've analyzed it. And we're going to look at some mathematical concepts that are going to be really useful for the rest of the year. And we're also going to talk about how Newton's second law, which is what we just basically described in the experiment, is written mathematically. Okay, so this is a deeper look at Newton's second law and the experiment that we did. Hopefully, you'll be applying these concepts when you write the conclusion part of your lab report, because in the conclusion, you're going to be making a claim about the relationship between force and acceleration, and you should be able to reference in the reasoning section that this result makes sense because of the of Newton's second law and because of the equation and the facts that we're going to be learning right here. Okay, so we're actually going to start by talking about some mathematical relationships, two different types of mathematical relationships. The first one we're going to talk about is the direct relationship. A direct relationship is where when one variable increases, the related variable, the other thing you're talking about, will also increase. Okay? And so here's an example of a direct relationship. Your focus on these notes and your grades on the quizzes that follow. So if you focus very carefully on your notes, if that is high, then the grade on the quiz should also be high and it should go up. On the other hand, if your focus on the notes go down, your grades on the quizzes should also go down. That is an example of a direct relationship. If we were to graph that, it's going to create a straight line with a positive slope, and you can see that here in purple. So we've got grade in percent over here, we've got focus in percent over there. If your focus is 10%, your grade's 10%. If your focus is 20%, then your grade is going to go up to 20%. Notice if we double the focus, we're going to double the grade. So that is what a direct relationship looks like on a graph. Most likely in your experiment, you found a direct relationship between increasing the force on your cart and its acceleration. Okay. An inverse relationship, on the other hand, is kind of the opposite of a direct relationship, but kind of not. This is where one variable increases, just like before, and the related variable will decrease. So that explanation is exactly the opposite of a direct relationship, all right? So distractions in class, if the distractions in class increase, then you're going to have a decrease in your grade on the in-class assignments. Whereas if your distractions in class are decreased, if they go down, then you're going to have better grades on your in-class assignments. That is an inverse relationship. If you graph this, though, you start to see that it's a little bit different from a direct relationship and actually a little bit complicated, because this is going to create a curved line that slopes downward and has what we call a limit at 0. What a limit means is that this line is going to get closer and closer and closer and closer and closer to 0, but it doesn't actually touch 0. It just gets smaller and smaller and smaller. And you can see that mathematically here. So if you've got one distraction in class, your grade's going to be like an 80%. If you double that to 2 distractions in class, what happens is your grade goes down by 1/2. So you doubled your distractions and you had half the grade. If you then increase your distractions to 3, so 3 times the distractions, then your grade is going to get cut in half again. That's actually the wrong number, I just realized. That should be 1/3 of 80, whatever 1/3 of 80 is. All right, but you get the basic idea that the number is not decreasing the same amount every time. It's not a straight line, it's a curve. Okay, and that is an inverse relationship. Okay, so you need to know these 2 kinds of relationships. They're on the word wall in our classroom. We're going to use them again and again and again, and we're going to talk about them again in just a second. Another math concept for you. So in physics, we work a lot with what I'm calling 3 variable equations. And in fact, these are all of the 3 variable equations for the whole class right here. So starting with 2 that you should have probably seen at some point, which is velocity right here equals the change in position over time. That's 3 variables, right? 1, 2, 3. Same for this equation about acceleration. This is also 3 variables. Force, mass, acceleration. 3 variables. All right, over here, 3 variables, 3 variables, 3 variables. This one has a constant in it, a number 10, but there's 3 variables, u, g, m, and h. Okay, still a 3 variable equation. This is also a 3 variable equation. Yes, it has a exponent in it, but that doesn't change the fact that there's 3 variables there. Okay, this one has a big old constant and an exponent, and it's kind of confusing, but guess what? It is still a 1, 2, 3 variable equation. All of these guys over here, 3 variable equations. This one, also a 3 variable equation. All right. In fact, I'm sure that every single equation in this class can be written as a 3 variable equation. All right, so we're going to learn a little bit about 3 variable equations right now. First thing you need to know about 3 variable equations is that you should be able to rearrange those 3 variables using algebra. So if you don't like the way that it's written, you need to be able to change that. So if you start with this made-up equation, A equals B times C, maybe you don't want to solve for A. Maybe you want to solve for B. Well, what you should be able to do is divide both sides by C, like we did here, because the fundamental rule of algebra is if you do something to this side, then you also have to do it to that side. Okay, so here I'm dividing both sides by C. The C's are going to cancel out right there, and that gives me this equation, which is much more useful if I'm trying to solve for B. On the other hand, I could do the exact same thing to solve for C. So if I want to solve for C, I have to divide both sides by B right here. The B's are going to, or I have to divide both sides by B right here, sorry. The B's are going to cancel out, and I'm going to get this equation, which allows me to easily solve for C. Over here, if I start with an equation that has a fraction, let's say I want to solve for A. Then what I would do is I'm going to multiply both sides by B, because again, the fundamental rule of algebra is whatever you do to one side, you have to do to the other side. The B's are going to cancel out right here, and I'm going to be left with this nice equation that is already solved for A. Okay, notice that I can do that without even plugging in numbers, and that's helpful in letting me identify what kinds of relationships we have. All right, so let's say we're looking at a 3 variable equation that is in this format. Something equals something times something, which is really what most of our equations are going to look like at this point. Newton's second law, which we're going to learn about in a second, the equation for momentum, the equation for impulse, the equation for kinetic energy, the equation for gravitational potential energy, all of these equations we're going to use in this term all follow this format. So we're going to learn about how to use this, okay? So First, we're going to pick the two variables we'd like to talk about the relationship between, because we can only really talk about relationships between two variables at a time. So we've chosen A and C. If these are separated by an equal sign, which they are, look, here's A, here's C, there's an equal sign in between. What that tells us is that these variables have a direct relationship. And let's take a second to talk about why that is mathematically. So here's why. Remember, the fundamental rule of algebra is whatever you do to one side, you have to do to the other. So let's say I double variable A. I multiply it by 2. Well, if I multiply this side by 2, what do I have to do to this side? Well, I have to double it also. So because they're on other side, sorry, you do need to write this into your notes real quick. If I double one side, I have to double the other. So that creates a direct relationship whenever there's an equal sign in between the variables. Okay? Here's an example. If C gets really, really big, then A also has to get really, really big in order to make the equation work. Now, this does assume that B here is not changing, that it is constant, but we just said we were only looking at the relationship between this and this. That's fine. You can think about it like an experiment where this might be the independent variable, that is your constant, and this might be the dependent variable. Okay? Over here, we see the same thing. So this is constant right here. And if this is your independent variable and it's decreasing, then this is going to be your dependent variable. And it is also decreasing. That is a direct relationship. If, on the other hand, you were to pick C and B, they are on the same side of the equal sign, as it says right here. And so they don't have a direct relationship. You can probably guess what kind they have. They have an inverse relationship. Okay. Let's talk about why that is mathematically. Well, sorry. So in this situation, remember that we're keeping A constant. So if this side of the equation is not going to change, then the other side of the equation also cannot change, or they would not be equal. So if I double variable C, if I multiply it by 2, then I have to divide variable B by 2 in order for this to remain the same, and therefore it still equals A. Okay? So make sure you've written that down in your notes also. All right? Over here, we have another example. So this time, we're saying that this is your constant. And if this was, I don't know, it doesn't matter, your independent variable, and it's decreasing, then your dependent variable over here is going to increase in order to make your constant remain constant. Okay, so now we're going to look at the very first three-variable equation in this class, and possibly one of the most important three-variable equations in physics. This is called Newton's second law. Newton's second law is usually written as this equation. F net, okay, this is the net force on an object measured in newtons, equals m, which is the mass of the object measured in kilograms, times a, which is the acceleration of an object. And acceleration, as we learned previously, is measured in meters per second squared. Okay. So, as we mentioned before, any things that are on opposite sides of the equal sign are going to have a direct relationship. So, for example, net force and acceleration are on opposite sides of the equal sign, and so they have a direct relationship. Okay, here's an example of that. So if you have a car and you apply the force of the brakes very gently, that car is going to slow down. Slowing down is an example of acceleration, very little. On the other hand, if you apply the force of the brakes very strongly and you have a big force, net force in this case, then you're going to have a big acceleration and the car is going to stop very quickly. Okay, notice that in these equations, mass is constant. Okay, on the other hand, or to take that a little bit further, right? So the less we apply the brakes, the less acceleration we get. The less force, the less acceleration. So if we take that to the extreme and we say that the net force is 0, and this is very important, then the acceleration will be 0. Okay? So if you don't apply the brakes at all, and there is no net force on the car, right? These things cancel out. There's absolutely no acceleration, and that means that this car will continue to move at constant velocity. This is something you learned about in junior high. It's called Newton's first law. We're going to talk about it more. Remember that in junior high, you learned that objects in motion stay in motion unless acted upon by a force. So in this case, there is no force, and so this car is just going to stay in motion. You might think to yourself, well, that's weird, because if you don't actually have to hit the brakes for a car to slow down. They slow down on their own. That's because there's another force of friction that we're not talking about. But if you can totally eliminate the force, which is what we did here, then you're going to have no acceleration, and that car is going to travel at that speed forever. All right. Let's look at some other variables. Okay, so force and acceleration and mass, acceleration and mass are on the same side of the equal sign. So they do not have a direct relationship. They have an inverse relationship, as it says right here. Okay, just to make sure that we keep this all straight, I actually want us to go back to where we said net force and acceleration have a direct relationship, and I want us to color code those. So we're going to go net force, get a little bit bigger highlighter, net force and acceleration have a direct relationship. And we said that if the net force is 0, the acceleration will be 0. Now down here we're talking about acceleration and mass have an inverse relationship. I like to use those color codes because we're talking about different things. We don't want to get them confused, okay? So now we've got this car speeding up. The car has a relatively small mass, and so it's going to have a large acceleration. This is why race cars are small and light. On the other hand, this truck may have the exact same force. They might have the same engine. You could think about like a Dodge Hellcat, where they sometimes put that same Hellcat engine into, big Ram trucks. And they might have the exact same force, so that's constant. Okay, but that doesn't mean that the other variables are constant. So if we have a much larger mass here, then we're going to have a much smaller acceleration. Truck can be super powerful. It doesn't matter. It's also super big. And so it's going to accelerate very slowly. All right.